Now that we know the basics of vectors, we can finally put everything together and analyze vectors in a more systematic way. That is, by using algebra. The topics of this video are going to be how we get the vector components if we know the magnitude and the angle of a vector, how we can get the magnitude and the angle of a vector if we know the components beforehand, and we're going to close as usual with a couple of examples. So let's get started. First of all, let's define what a vector in standard form is. And a vector in standard form is always represented in the xy Cartesian plane by placing it with its tail at the origin. So let's say that we're dealing with a vector in the first quadrant, like so. We have the x and y coordinates here, and the angle is always taken to be positive if it's measured counterclockwise with respect to the positive x-axis. So in this case, this angle here, it's a positive angle. If we were to measure it clockwise, the angle will be negative. I'll give you an example of clockwise angles in the examples. Now let's do the following thought experiment. Let's assume that the x and y coordinates are both screens, and the a vector represents a barrier dividing the two. Let's say first of all that we shine a light from above onto the x-axis. Now that light will be partially blocked by the vector a, which will cast a shadow on the axis, like so. This shadow here is called the projection of a onto x. But we don't call it the projection of a onto x. That's too long of a name. So we just label it ax with a subscript x. Now let's imagine we do the same thing on the y-axis. We shine a light now, but towards the y-axis, and that will be partially blocked also by the a vector, casting a shadow on the y-axis like this. This is also known as the projection of the vector a onto the axis y, which you label as ay. Now ax and ay are known as the components of the vector a. Now the question is, how can we get ax and ay if we know the magnitude of a and the angle? Well, first of all, we can do the following thing. Ax and ay are not just length. They can be thought of as vectors themselves. And therefore, because they're vectors, we can slide them around as long as we don't change their direction or we don't change their length. So we're going to do precisely that. We're going to take the vector ay and slide it here. But now we see something interesting. The three vectors here represent a right angle triangle whose legs are the magnitudes of ax and ay, and whose hypotenuse is the length of the vector a. And we know very well how to work with a right angle triangle. So we can write down in two lines how to express the ax and ay components in terms of a and the angle theta. For ax, because it is adjacent to the angle, we know that it's given by the magnitude of a times the cosine of theta. And ay, because it's opposite, it's given by a times the sine of theta. This set of equations here allow us to determine, if we know the magnitude and the angle, how to get the components ax and ay. Now the question is, what if we have the components? What if we were given ax and ay and we wanted to find the magnitude a and theta? Is there a way to go backwards? Let's say we know ax and ay and we want to go backwards and obtain a and theta. And the answer to this is yes, there is a way. And the only thing we need to use is the fact that AX, and AY represent the hypotenuse and the legs of a right angle triangle and our knowledge of trigonometry. By doing that, we see that we can write A through the Pythagorean theorem as the square root of AX squared plus AY squared. But what about the angle? We don't have an expression for the angle. We do have, however, an expression for the tangent. We know that the tangent of the angle theta, if we know the two legs, is given by the opposite, in this case AY, divided by AX. Well, that doesn't give you the angle, but it gives you the tangent of the angle, which is a function. And even more importantly, tan is a function that has an inverse, or an invertible function. What do we know about functions from algebra? If you have a function, f of x, and you know that that function has an inverse, then you can take the inverse of that function, or the composition of the function with its inverse, and we know that that gives us back the argument. Well, what that means is really that if we know tangent, we can take the inverse tangent, and that will give us the angle itself. Let me write it down to make it clear. If we know the tangent of an angle, we can take the inverse tangent of the tangent of an angle, and that gives us the angle itself. So what does it do to this equation here? Let's write it on the left here. If we take the inverse tangent of this equation here, we get the inverse tangent of the tangent of an angle is equal to the inverse tangent of this ratio here, AY over AX. But we just said that the inverse tangent of a tangent is the inverse function of the same function, which returns the argument, so the left side is theta, and that tells us that theta is equal to the inverse tangent of AY over AX. But now, how do you calculate this inverse tangent? Is it something that you do by hand? No, not really. Your calculator has already embedded in it the inverse tangent function. So all you need is a knowledge of what AY and AX are, and you just plug them in your calculator and hit the button for tangent to the -1, and that will give you a number which will correspond to the angle. So we see that we also have a set of two equations here that give us, given the components, the value of the magnitude of A and its direction. Now I want to emphasize here an important point. Whether you know the components or you know the magnitude and the angle, you always, and this is very important, need two numbers to specify a vector. Why is it two numbers? Well, because we're dealing with vectors in 2 dimensions. If we were dealing with vectors in 3 dimensions, you would need 3 numbers, and more abstractly, if you deal with vectors in n dimensions, you would need n numbers. But for us, we're never going to do that, so all that we need to understand is that there's a way to go from the magnitude and direction to the components, and another way to go from the components to the magnitude direction. But the key point here is that you always need 2 numbers. Now there is a problem here with the way that we define the tangent, because we were working in the first quadrant. And in the first quadrant, both the x and y components are automatically positive because we're moving along the positive x-axis and also along the positive y-axis. If we looked at the other components, things change a bit. For instance, in the second quadrant, the x component is negative because we're moving along the negative axis, and the y component is still positive. In the third quadrant, both of them are negative because we're moving along the x-axis, and along the y-axis. And in the fourth component, x is already positive and y is negative. Why is this important? This is important because in our calculation of tan inverse, we're taking the ratio of ay over ax. This ay over ax can be either positive or negative. So let's look at it. If it's positive, that means that both ay and ax are positive, in which case you're in the first quadrant, but it could also be positive because both of them are negative, in which case you're in the third quadrant. If it's negative, you're in the other two quadrants, namely you're in the second quadrant if ax is negative and ay is positive, or you're in the fourth quadrant if ax is positive and ay is negative. The problem here is that your calculator does not determine this. Your calculator will give you a number because the calculator doesn't really know which one of the two numbers in the ratio was negative. So it's up to you when you solve the problems to determine in which quadrant you are in order to determine the actual angle that you're measuring. Again, I will show you this in the example at the end. So let's start with one example here. Let's say that we have a vector of magnitude 8.09 meters, and we know that it makes an angle of 14 degrees with the positive x-axis. And we want to determine the components. So we know in this case that A is 8.09 meters, and theta is 41 degrees. We want to determine what ax and ay are. In order to do this, we only need to apply the two expressions that we just derived. Ax is equal to a cosine of theta, which is 8.09 meters, times the cosine of 41. Now be very careful here that when you use your calculator, you have your calculator in degrees and not in radians. And when you plug in the numbers, you get 6.11 meters. I always give you the answers because I want you to verify yourself that this is the answer that you get. And in fact, it will be a great thing if you pause the video at this point before watching me solve the problem and solve it yourself. Likewise, for the y component, we have a sine of theta, which is 8.09 meters, times the sine 41 degrees, which again, when you do your calculation, gives you 5.31 meters. One way to verify that you're actually getting the correct number will be to work in reverse and at least check the magnitude. For instance, you know the magnitude is equal to the square root of the sum of the two squares. So by plugging the numbers, you should get something that's very close to 8.09 meters. I'm not saying identical because there can be a rounding that changes the number. So I'm going to let you do the second part of this exercise. Now let's move on to a second example here in which we're given the components x and y of a certain vector, and we have to determine first of all the quadrant in which the vector lies and then find its magnitude and direction. It really helps when you do a problem like this to draw the vector. Even if it's obvious, it's just good practice to do it. So if you were to draw this vector here, you know that the x component is a negative number and the y component is a positive number. So you will start by drawing an xy plane, and then you will draw your vectors. If ax is negative, means that you're on the negative x-axis, and ay is positive, in which case you're there. And so we see that the vector is in the second quadrant, and it has to be a vector that points in that direction. This is our vector A. First of all, we want to determine the magnitude. That is obtained through the Pythagorean theorem. A is equal to the square root of ax squared plus ay squared square rooted. And notice that this ensures that whether the components are negative or positive, the number that we get out is always a positive number, as it should be. So when we plug in the numbers, we get 3.57 meters squared plus 5.21 meters squared. And again, you're going to verify this, but if you do it correctly, you get 6.32 meters. Now, what about the angle? Let's think about it first. This is the angle that we're trying to find. It's always the positive angle with respect to the x-axis measured counterclockwise. Now we know the two components, so we plug in the numbers in our expression, tan inverse of ay over ax. But this ratio here is going to be negative because this is tan inverse of 5.21 meters divided by negative 3.57 meters. So when you plug this into your calculator, if you have it in degrees, you're going to get the following. Negative 55.6 degrees. And then you're going to scratch your head and say, wait, why am I getting a negative number? You're getting a negative number because really your calculator is seeing a negative argument for the inverse tangent, and it's giving you not the counterclockwise angle, but in fact, it's giving you in this case, this angle here. So this is the angle negative 55.6. Why is that angle negative? It's negative because it's measured clockwise. So in order to determine what theta is, you have to remember the fact that if you have this angle here between the positive and x-axis, it's 180 degrees. And so you have to do 180 minus 55.6, and that gives you 124.4 degrees, which is in fact the correct angle that the vector makes with the positive x-axis. Now there are other ways of doing this. This is not the only way. Another way would be to take the absolute value of the argument of the inverse tangent to avoid that there is a negative in the result, and then determining always from the graph where the vector lies and determining whether we're adding that number to 180 or 270 or subtracting it from 360. Now all methods are equal to one another in the sense that if you do them correctly, they lead to the right answer. But at the bottom of all of this, there's always the understanding that you shouldn't trust your calculator by plugging in the numbers. You should always think carefully about what you're doing and then determining the answer from that. I hope you found this video useful. In the next video, we're going to talk about vector addition using components in algebra.